Okay, welcome back, guys. Last lecture for the week, Nullspace. So let's get started where we left off. If A is a M by N matrix, then the set of all solutions of the homogeneous equation AX equal to the zero vector, right? That's what we mean by homogeneous, is just our matrix equation set equal to zero, the zero vector, is a subspace of Rn called the null space of A. Denoted with a cursive N of A, null space of A. Right? I like to think of the null space of A as kind of like the x-intercepts of a matrix. Think of the null space of A. It's not exactly the same thing, but it's close enough. You can think of the null space of A. The idea is that the null space of A is the x-intercepts of A times X, our matrix equation. Now, when you deal with x-intercepts, right, when we talk about x-intercepts in general, right, when we talk about x-intercept, suppose I have something like this. I have a function. I have f of x is equal to x squared minus 1. What are the x-intercepts? What do we mean by x-intercepts of a particular function? Well, the x-intercepts are what's the values of x that make the function equal to 0, right? So, in this case, what are the x's? What are the x-intercepts? Right, we set this guy equal to 0, solve for x, so we get x squared is equal to 1, so we get x is equal to plus or minus 1, right? These are the x-intercepts of my equation. So when I plug in 1 into this function, I get 0. When I plug negative 1 into this function, I get 0. This is what we mean by x-intercepts. So when I say null space of A, right, I mean that when I multiply A times my x vector, I'm going to end up with the 0 vector, right? Just like when I plug 1 into this function, I end up with 0. When I plug my whatever my value of x is for my vector times A, I get 0 back. I hope that kind of makes a little bit of sense. Let me show you an example. See if I can squeeze it over here. Determine whether B equal to 0, it's like negative 1, 0, and W equal to 464 are in the null space of A. If A is equal to 1, 0, negative 1, 1, negative 2, 2. So essentially I want to know, when I multiply A times that vector, do I get 0 back, right? Well, essentially, well, it goes to the value of 0, right? Does it act like an x-intercept? So that's what I want to do. So the first thing I need to do is multiply A times B and then A times W, right? So let's do A times B. So A times B, let's see if I'm going to squeeze in here. Again, I apologize, but I'll try to make it big enough. Hopefully camera quality helps. Oh, well, I can't squeeze both of them in there. Oh, well, that's okay. Life will go. So I have 0, -1, 0. So I have 1, 0, -1, and I'm going to multiply that times 0, -1, and 0 using the dot product, right? What do I end up when I do that? I get a 0, which is good. That makes me happy. When I take 1, -2, 2, dotted with 0, -1, 0, what do I end up with? I end up with a value of 2, which does not equal 0, by the way, the 0 vector. So that means that B is not in the null space because it's not an x-intercept. And again, I'm using the idea of x-intercept loosely, right? Meaning that if I multiply that A times that vector, I get to 0 vector. Just like when it's like if I'm like plugging in that vector times A, right, to get and see if I get 0 when I do that. What about W? Let's look at that one. So I have A times W, A and W root here, good root here. Might be hard to find these days, I don't know. 1, 0, -1. 1, -2, and 2. Times W, which is 464. Yeah. First row. Dotted with our column here, we get 4 minus 4, which is 0. Off to a good start, but we were off to a good start the last time as well. And the next one's going to be, what's that? 4 plus a negative, so that's plus a -12, plus 8, that gives me 0. This is equal to the 0 vector. So when I do A times, I plug in W, right? That's my X value. A times W gives me the 0 vector. So that tells me that W is in the null space. So the null space of A is going to be all possible values of my vectors, all possible vectors that when I multiply times A, I get the 0 vector back, right? Here, like in this x-intercept, right, all possible x-intercepts of this function are going to be plus or minus 1. These are all the possible solutions in which this function will be equal to 0, right? So this will, you can think about this guy as being like the null space, right? Null space of this function. All the possible values that will make that function 0, right? All possible values of x. Now the question is, how in the world do we find the null space of A? And that's easy enough. We just need to solve the matrix equation. Just like we did here, right? When we did this function, right? I set this guy equal to 0 and I just solve for x. I mean, that's pretty straightforward, right? We're gonna do the same thing. If I want to find the null space of A, right, I just need to set AX equal to 0 and solve for x. So that's what we're gonna do. So to find a basis for the null space of A, solve AX equal to the 0 vector. That's all we need to do. Solve AX equal to the 0 vector. Of course, for the value of x. So here's an example, just kind of using the last matrix we had before, not the one here, but the bigger one. This one's in your book, so if you don't want to write it down, you don't have to. But it's good to kind of write it down anyway, take notes. So we get 1, 3, 1, 3, 0, 1, 1, 0, negative 3, 0, 6, negative 1, 3, 4, negative 2, 1, 2, 0, negative 4, and 2. So this is my matrix A. And I wanted to find a basis for the null space of A. Right? I want to find a basis for the null space of A. Essentially, all I have to do is create an augmented matrix. And if we've done augmented matrices enough time, we've done augmented matrices enough time where if we have 0 here along the right-hand side, right, that column of zeros when we do the reduced row echelon form never changes, right? We've done it many times. I like to put those zeros there just to kind of remind me that I'm dealing with a system of equations, right? But when I do the reduced row echelon form of a matrix that is a homogeneous system from a homogeneous system of equations, right, I really don't need to write that row of zeros. I just kind of do it just because to remind myself that it's AX equal to 0. And so I'm going to just kind of do that here. I'm just going to modify this. I'm just going to say there's zeros right here. Okay. And let's do the reduced row echelon form of this. When I take the reduced row echelon form of this equation, right? This is what I get, and we've already seen this before already, but I'm going to write it again. From the last class, we have 1, 0, negative 2, 0, 0, 1, 1, 0, 0, 0, 0, 1, and then I have 2 rows of zeros. This is what we get when we do the reduced row echelon form of A. And remember, since we're dealing with AX equal to 0, right, I have another column of zeros right here. Now, what is the system that we have here? What's our system based off of AX equal to 0? Let's just kind of read across, right? What is our system going to be for this? Once we have it in a reduced row echelon form, this should be, I'll call this x1, x2, x3, x4. So this becomes x1 minus 2x3 equal to 0. Okay. This is x2 plus x3 is equal to 0. This is x4 is equal to 0. Now, that's why I made sure to put this column of zeros here to remind myself that I'm dealing with x1, x2, x3, and x4, right? So this is not my last column, right? I have one more column that I'm dealing with here. What's my solution when we work this out? Solution. I have x1, x2, x3, x4. X4 is always 0. That doesn't change. What is x3 equal to? And the answer is anything it wants to be, right? So I'm going to call that t. What is x1? Well, x1 is 2t. And what is x3? X2. X2 is negative t. This is the parametric form of this solution, right? And what I'm going to do is just like we did with the eigenvalues and eigenvectors, right? I'm going to write this in vector form. And I'm going to have one representative vector to represent my solution here. So I have 2, negative 1, 1, 0 times t. Okay? So any multiple of 2, negative 1, 1, 0, right? And if you think about this, this is going to be my null space. My null space is going to be any multiple of 2, negative 1, 1, 0. This is a line. This is a line in what space? In R4. So if you said that, you're good. I know it's a line because I only have one independent vector, linearly independent vector. One linearly independent vector, so it's a line in R4. I know it's in R4 because it's has 4 components. Okay, it has 4 components. So I know that my null space could be, I could plug any multiple of 2, negative 1, 1, 0, multiply that times my matrix A, and I get the 0 vector back when I do that. And you should try it out for yourself. Take a multiple of 2, negative 1, 1, 0, multiply it times A, and every single time you're going to get 0 back. Okay. So what's my basis then? So my basis is just going to be that one vector. I can say the null space of A is equal to just the span of this one vector that I have here. 2, negative 1, 1, 0. So my basis is just going to be this one vector here, 2, negative 1, 1, 0. What's the dimension of my null space, right? And the answer is, my dimension is 1, because I have one basis vector. So my basis is this one vector that I have here, 2, negative 1, 1, 0, right? And then the span of that is going to be a line in R4. It's going to be a line in R4. The dimension of this guy, the dimension of my null space is 1. Now, there is a name. Just like the row space and the column space dimension had a name, which was the rank. The null space also has a name, which we call the nullity. Nullity. So nullity of A. Nullity of A. So you'll see it, you'll write out like this: nullity of A is equal to 1. So that's pretty neat. So what we're going to do is we want to do a couple more examples. And go from here. A couple more examples. Erase this stuff right here. I hope you guys are doing okay wherever you are, all over the country. I'm praying for you guys every day and miss you guys. Wish you were here. I know Buford and Genevieve are a good company, but you guys are much better company. Just no offense to Genevieve and Buford, which are my teddy bears. Let me write it down here. If A is equal to 1, 0, negative 1, 1, negative 2, 2, what is the null space of A in this case? What's the null space of A? Well, we're going to do the same thing we did last time. If I wanted to, just for the sake of space, well, I'll write it here. Have 1, 1, 0, negative 2, negative 1, 2, and then I could put 0, 0 if I wanted, or I could just remember that I have another column of zeros. It doesn't matter which one you want to do, okay? you guys are experienced enough that you can either add the zeros or not, as long as you remember that I'm dealing with a system, right? I want to solve AX equal to 0. The reduced row echelon form of this, when I work this out, see if I have it. I should have it somewhere here. Yes, I do. I have that it is 1, 0, negative 1, 0, 1, negative 3 halves, 0, 0. Now, I didn't say this before, but whenever I do a problem and you want to see if you can do the problem yourself, just stop somewhere. I know I'll probably continue talking just because I want to squeeze as many lectures as I can in this remaining time that I'm with you guys. But feel free to just pause the video and just work the problem. See if you're like, I can do it myself, Dr. West. I can do it. You don't have to hold my hand. Feel free to do that. What's my system going to be? Put here. So I get x1 minus x3 equal to 0, right? Get x2 minus 3 halves x3 is equal to 0. And let's write this. Let's just go directly to the vector form of the solution. Let's see if we can do that. The vector form of the solution, right? If we work this out, I get x1, x2, x3 is equal to, I only have one free variable, right? Which is going to correspond to x3. So I can write this as, I think, if I did this correctly, t, 3 halves t. Oh, that's a very ugly. 3 halves t. And the last one is, what is it, t? Usually you guys don't write it that way, right? You're like, Dr. West, we don't write it that way. So I'm gonna actually put the, this says 1, right? 3 halves, and then 1 again times t. Again, if you wanted to, I'm looking at all possible multiples of 1, 3 halves, 1, right? So if you wanted to, you can just look, if you don't like fractions, right, just multiply this vector by 2, right? Just multiply this vector by 2, right? Because I'm looking at all possible combinations of this. And again, this is going to be a line in R3. Let's say that first, line in R3. But if I wanted to, I'm going to say, okay, my null space of A is equal to the span of a single vector. I'm dealing with a line again. I'm going to multiply everything by 2 because I'm looking at all possible linear combinations of this vector. So I get 2, 3, and 2. I just multiply the entire vector here by 2. Again, I only have one basis vector in this case. So the nullity of A is equal to 1 in this situation. And I want to do one more example, but I want to talk about the rank nullity theorem, and then we'll do this last example, we'll be done for the day. The rank nullity theorem. If you guys remember, before we actually had the rank theorem, this is very much the same thing, right? Just a different way of saying it. And it says, if A is a m by n matrix, then the rank of A plus the nullity of A is equal to n. This is the rank nullity theorem. So the rank of A plus the nullity of A is equal to n. Now, before we do the last example, let's go back to the previous one, right? Here I have A equal to 1, 0, negative 1, 1, negative 2, 2. What's the size of this matrix? What's the size of this matrix? It's a size 2 by 3. Size 2 by 3, right? So what is n in this case? What is the value of n? Well, the value of n is 3. So I'm going to say from the previous example. A is a 2 by 3 matrix. So that means that therefore n is equal to 3. Okay, n is equal to 3. What is the rank of A? What's the rank of A? I know that n is equal to 3. What is the rank of A? And you say, Dr. Wesley, how can I figure out the rank of A? Well, you know the nullity of A. What is the nullity of A? The nullity of A is 1. We know that. Right here. So we know that the rank of A plus the nullity of A has to be equal to 3. Well, we know rank of A has to then be equal to plus 1 is equal to 3, so rank of A has to be equal to 2, right? So essentially, I know that my column space and row space have dimension of 2. I know that the column space and the row space has to have a dimension of 2 because the rank of A represents the dimension of the row space and the column space of A. All right, so here's my last example, last one, and we'll be done for the day. Just kind of bring everything together into one problem, and then we'll be done. This is one where you can stop the video and do it on your own. Make sure you know how to do it. Here it is. Last example. Find a basis for the row space of A, column space of A, and null space of A of A equal to 1, 2, 3, 4, 5, 6. Oh my goodness. 1, 1, 1, 1, 1, 1. 4, 7, 10, 13, 16, 19. Okay? I want to find a basis for the row space, column space, and null space of A. That's what I want to do. Intimidating, but we just take it. How do we eat an elephant, right? Old joke. One bite at a time. Ha ha. Right? Let's do the row space A. Hopefully you paused the video and you did it yourself. Take the reduced row echelon form of A. The reduced row echelon form of A is going to be, if you work it out, I have, if I did it correctly, 1, 0, negative 1, negative 2, negative 3, negative 4. Then I have 0, 1, 2, 3, 4, 5, and then I have all zeros. So my basis for the row space of A, basis for the row space of A are going to be two vectors. 1, 0, -1, -2, -3, -4, just going down. And the other one is 0, 1, 2, 3, 4, and 5. Okay. The column space of A I need to do A transpose, right? So I'm not gonna type I'm not gonna write A transpose down. I'm just gonna say the reduced row echelon form of A transpose. What is that gonna be equal to? The reduced row echelon form of A transpose. I get this 1, 0, 3, 0, 1, 1, and then I have everything else is zeros. So I have 4 rows of zeros. I look at the non-zero rows of A transpose, right? Non-zero rows of A transpose, 1, 0, 3, and 0, 1, 1. So my basis for the column space of A are going to be two vectors, 1, 0, 3, and 0, 1, 1. 1, 0, 3 and 0, 1, 1. All well and good. Now notice that these guys have both the same number of basis vectors, right? This has two basis vectors for the row space of A. This has two basis vectors for the column space of A. What's the rank of A? Rank of A is equal to 2. Let's box all of these guys, right? Basis, row space, and column space. I'll even box the rank. Now that I know that the rank of A is 2, now that I know the rank of A is 2, right? What is going to be the nullity of A? Okay. And that is going to be the size number of columns I have. So let's see, how many columns do I have? 1, 2, 3, 4, 5, 6. So I have 6 columns. That's going to be my n. N is equal to 6. I have rank of A is equal to 2, so 6 minus 2 gives me 4. 4. So here my row space of A is going to be a plane in R6. This is going to be a plane in R3. The null space of A, what is that monster going to be? It's going to be 4. It's going to be a 4 space. Define the null space of A, right? Define the null space of A. Remember, the null space of A, just remember. The null space of A is just going to be me solving for the matrix equation AX equal to 0. It's essentially like me adding another column of zeros here, right? So I have A times X equal to 0, right? Then I do the reduced row echelon form of that system. I get this, right? And now I want to find out what is going to be my values based off of this reduced row echelon form. So I'm going to just going to use this reduced row echelon form I have right here. I don't have to do any more work, right? When I take the reduced row echelon form of A and A transpose, then that gives me the row space and column space basis, right? And then I just tack on the zeros at the end of my reduced row echelon form of A, right? To figure out what the null space is going to be. So let's do it. Let's see what we get. We get that my system is x1 minus x3 minus 2x4 minus 3x5 minus 4x6 is equal to 0. Then I get x2 plus 2x3 plus 3x4 plus 4x5 plus 5x6 is equal to 0. That's my system. What's my solution? I have x1, x2, x3, x4, x5, x6. Right? Let's remember that. Whew. What are my leading variables? Just remind ourselves, what are our leading variables here? Our leading variables are x1 and x2 equal to, x1 and x2 are our leading variables. Sorry, x1 and x2 are our leading variables. What are our free variables? x3, x4, x5, x6, right? And they're free to be whatever they want to be. They're going to be our parameters, right? So say x3, we'll call it r, s, t. Oh goodness, I need another letter. What's a good letter? P? I don't know. P. Just made something up. P. All right. And now what is x1 going to be equal to? x1 is going to be equal to r plus 2s plus 3t minus 4 plus 4p. Okay. x2 is going to be negative 2r minus 3s minus 4t minus 5p. Okay. And so if I write this in as a vector, right? Let's do it here, vector form. This is a big one. I have one vector that's going to be multiplied times r, right? One vector that's going to be multiplied times s. One vector that's going to be multiplied times t. And one vector that's going to be multiplied times p. Each one of these vectors is going to represent my basis. One of my basis vectors, right? Notice that I have four vectors, right? One for r, s, t, and p. That corresponds to my nullity. So let's write it down. Let's see if we do it right. You guys just double check, make sure I do it right. Sometimes I might have an error here or there. I'll try to avoid that, but that might happen. So we just have to deal with that. It does. So r, I get 1, negative 2, 1, 0, 0, 0, right? For s, I get 2, negative 3, 0, 1, 0, 0. For t, I get 3, negative 4, 0, 0, 1, 0. And for p, I get 4, negative 5, 0, 0, 0, 1. So my basis for the nullspace of A I'm going to have to write them on their side here. Just to squeeze them in there. Do I have enough space to write them on the side? No. I'll just write them here. Or our same guys that we have here. 1, negative 2, 1, 0, 0, 0. 1, negative 2, 1, 0, 0. Oh, sorry. I did it repeated twice. 2, negative 3, 0, 1, 0, 0. 3, negative 4, 0, 0, 1, 0. 4, negative 5, 0, 0, 0, 1. Okay. That's the null space of A, basis, the null space of A. The null space of A is going to be a 4 space, right? This is going to be a 4 space and R6, right? 4 space and R6. That's what we're looking at here. is going to be the nullity here? The nullity of A is going to be equal to 4, which is what we said. So that is the last example for the day, right, of this lecture. And we're going to pick up with a new topic next week. See you guys then. Bye. I hope you guys are doing well.